Hi everyone, my name is Natan Kaplan, City of Holo, and thank you for joining me today for my talk about flexible beam shaping for high power laser beam shapers, for high power lasers. So today I'm going to talk about macro processing. Usually I talk about microprocessing, you know, applications such as scribing and laser liftoff and drilling. But today I will talk about macroprocessing, welding, cutting, multi-kilowatt applications, a lot of fiber lasers going into this field today, a lot of exciting opportunities. And I think we at Holor have a lot to offer. So first of all, who are we at Holor? We are a diffractive optics manufacturer that specializes in high power beam shaping. We have been in existence for more than 30 years, and we work with all wavelengths from the deep UV up to the mid IR with a specialization in precise design and manufacture of diffractive optics. Now, we were the first company to deliver DOEs for commercial use, and we continue to develop various solutions to fit the market needs for any sort of applications of shaping of high power laser beams. So basically, for those that are not familiar with them, DOEs or diffractive optical elements are phase gratings or phase structures that can impose any phase on the laser wavefront. By etching these structures directly into the substrate material, we ensure high LDT and durability to high power lasers. And by using a sort of semiconductor based binary or multiple binary exposure production process, we can achieve unparalleled accuracy. Basically, our DOEs have no tolerances on their angles. So they are precise, they have no thermal effects, thermal lensing, or such effects that can change their shape due to temperatures, and they are very suitable for work with multi-kilowatt lasers. Another advantage compared to standard lenses or refractive modules is the fact that DOEs are thin and compact. You can basically, the active layer is a few microns on the top of the DOE, and this layer does all the shaping. You do not need large distances or bulk. And the last advantage, which is, I think, the interesting one for today, is the fact that DOEs can combine multiple optical functions. So basically, DOEs can do a lot of things to the light. The main families that Holors deals with are the beam splitters that split the light into an array of beams with controlled separations, the beam shapers that shape a laser beam into a predetermined shape, for example, a square, a circle, or any other arbitrary shape. This shaping can be done either through analytical beam shapers for single mode lasers, which has basically no speckle and high efficiency and continuous surface, or through diffractive diffusers, which are very precise and have very sharp transfer region, better than most micro lens arrays. And the last family is the focal beam shapers that can manipulate the intensity in the focal direction in transparent materials. For example, creating bezel-like beams, splitting the focus into multiple foci, and other types of manipulations. Today, specifically, I want to focus on the applications of beam shapers for the welding, cutting, and additive manufacturing industries. Now, we have seen in the last few years a lot of interest in processes that are macro processes done by laser due to efficiencies in economy, ecology, and the increasing e-mobility revolution. All these sorts of applications, for example, welding of battery packs and contacts for batteries, cutting, of course, it's always a major industrial application for high power lasers. All these applications are reaching the point where laser power itself is no longer the limit. Basically, now there are high power lasers available from sources in China and other places that are not very high cost and can provide energies in excess of 1 kilowatt easily. And the process throughput, the speed you can cut, weld, or sinter the particles, for example, they are no longer limited by the power. I mean, theoretically, you would say, yeah, I can just do it faster. I will increase the power and move faster. In reality, it is not so simple. What happens is that you start to have a lot of process related failures that are things such as bubbling, cracking, spattering of the material that ruins the weld quality, for example, and all these sorts of limiting processes that are not directly related to the energy of the laser, and they limit the speed that welding can be done. Now, of course, we all want faster welding because faster welding is more cost effective, and better welding for the same reason. And one of the solutions that was developed in the, let's say, last 5 years, it's gaining more and more prominence, is by using shaped illumination. There are many shapes that are used. Let's say the most popular one, the one we're seeing the most, is what we call the ring with a central spot. There are, of course, other shapes that are optimized for other processes, such as the brazing shape you see in the upper right here, and the C shape that we have done in the Taylor Weld project with MTC and other but generally, various shapes can achieve better process throughput and better speeds by stabilizing the melt pool. The idea is that by illuminating the melt pool in the melt area, you can create a suppression of sputtering and a sort of thermal annealing or preheating of the weld area or the cut area so that there are less of these effects that limit your throughput and you can achieve a higher rate. Now, generally, the, let's say, industry standard solution, or what is starting to emerge as a solution, is the use of shaped core fibers. Important, but let's go back for a second. An important thing to say is that for each process, for each material thickness and type of process, there is a different ratio of, for example, central spot to ring intensity. But in our experience, and based on the feedback we're hearing from many customers, there is no need to change this ratio once the process parameters are set. Usually, these machines work on more or less the same set of parameters and the same sort of materials. And once you find this ratio by adjusting it and finding some ratio that works optimally for the process, there is no need to change it. Now, the way this sort of shaping is usually done now is by multi-core fiber solutions. There are many solutions by most leading laser companies. I would not say names, but these solutions are based on the idea that you have basically several lasers. They share the same fiber geometry, but you are pumping separately the internal core and some other larger diameters concentric cores, and you can switch them electrically, which is very convenient, to provide you some power in the center, some power in the external ring, and various ratios. Of course, the central is limited to a certain level of power, while to get above that, you have to switch on the ring. So the tunability is limited. Of course, and one of the main advantages that's basically it comes out of the fiber. You just integrate it directly into the system, and theoretically it works. But when you have these higher diameter rings, it means that the laser has a higher NA. You need larger optics in your welding or cutting system compared to working with a lower NA multi-mode fiber that doesn't have this sort of ring structure. So we have seen this sort of solution emerging. And as I've said, we have not seen any demand from our customers for rapid switching. This sort of switching is usually done still in the millisecond scale. But we have developed a separate solution that is suitable for this same sort of multi-ring shaping and is based on a much simpler and, let's say, straightforward concept. The idea is that we, with our flexible solution, the Flexishaper, we can create the same sort of shaping that is done from this sort of multi-core fiber by utilizing just two simple binary straightforward DOEs. By rotating these two DOEs so that the phase regions either overlap or do not overlap, we can get the full range tunability from all the power of the laser in the central spike to the power in the ring. And the main advantage here is that the adjustment is just simple rotation. You can just mount it on any motorized rotation stage or even manual rotation stage. And by simply rotating it, you can get the full range of adjustment. Now, this is not just some theoretical construct. We have produced these elements. We're cooperating on showing this with high power. We've measured them at lab. And you can see that we can get the full range tunability from all the energy in the center to almost all the energy in the ring in 15 degrees of rotation. This was done with a 1064 laser. And one of the main advantages with our Flexishaper concept compared to the multi-core concept of doing the shaping in the laser itself is the fact that you can integrate it into existing systems and you can use it to shape single mode lasers, not only multi-mode lasers. You can get adjustable shaping in single mode lasers, for example, for applications such as micro welding and precise welding, and still gain the advantages of the ring with central spot and adjustability. Another advantage of this sort of shaping is its high efficiency. You do not need any, you do not have basically do not have any major losses other than a weak arrow outside, which is also sort of preheating the material. And it's much easier to integrate compared to the larger optics needed with a multi-core fiber. With a multi-core fiber, from the collimator, you already need larger optics because the NA is higher. So you have to handle that with basically larger optics, and it has to be along all the optical path, including the focus system. Our module can be integrated really close to the end of the system, near the focuser, the final focus towards the surface. And by this way, you can use smaller diameter optics, cheaper, easier to adjust, and much easier to integrate along the entire system. So in summary, the Flexishaper that Holo has developed is a simple concept based on two diffractive same elements that one is where one is rotated versus the other. By rotating them, we can get full range adjustability between a central spike and a ring, getting the same sort of process benefits as a multi-core fiber, but you can get that with any simple fiber. You can just buy a multi-mode fiber laser, which is also lower cost, and get the same sort of process benefits. It has the full range adjustability. You don't have to settle for having, I don't know, 8 kilowatts in the spot and 15 kilowatts in the ring as the maximum. You can put 22 in the central spots and 2 in the outside ring. It has high LDT because these are etched optics that are passive. Nothing is moving there. It's not based on SLMs or anything like that, just etched optics. And it's also suitable for single mode for applications such as micro welding or precise sintering, where the multi-core solution is only multi-mode, basically. Thank you for listening to my talk.